the inverse, the Laplace transform. So, and this chapter will discuss how to inverse the Laplace transform to the time domain functions. Let define the very general form of Laplace transfer function Fs is numerator and denominator. So it will be expressed is in a form, for example, Sn plus an minus 1 Sn minus 1 plus an minus 2 Sn minus 2 plus blah blah a1 s1 and plus a0. The numerator will be bm s m plus bm minus 1 s m minus 1 and blah blah b1 s. Oh, I'm missing this s and b0. This will be a very general form of the Laplace, the transfer function. So the d is a denominator, denominator in Korean, and n is the numerator in Korean punja. So we define let all a and all b is a real number. That means this is this will be the rational function. With as much as that here we already know about the pole and zero. The same terminology will be used here. So we define that there are two equations. First is denominators 0. So we call that this is the solution of this is we call pole. And numerator s is 0. So we call this is the solution of that. The root of this is 0. So we can say the pole, the pole will be like that. The ds is 0. That means ds is in power n, an minus 1 sn minus 1 plus a1 s1 plus a0. So there will be some solutions. We define that we will replace it this time is s minus p1, s minus p2, s minus pn. Then pi, we call this is a pole. The pole would be a complex number. In other words, in other way, 0 will be ns So bmsm plus bm minus 1 sm minus 1 b1s plus b0 will be 0. So the same way it can be represented is s minus g1, s minus g2, blah blah, and s minus gm and bm will be 0. So we call gi, we call this as 0. So then it will be complex number. But in the Phaser, the pole is kind of a j omega. So that means that there are only the imaginary terms. But in the Laplace, the point 0 is a complex number. So the Phaser approach is kind of a subset of the Laplace approach. So here we will do this, how to inverse the Laplace transform, Laplace functions. And first, Fs transfer the present as the partial fraction and expansion. Partial fraction expansion means that we will represent f as will be f1s plus f2s plus blah blah in this manner, fns. And second, inverse transform h fis. Then final ft with the sum of this, the each fs is inverse transform. So f1t plus f and t. So that's very simple, but the new things here is what is the partial fraction expansion. So we will discuss about some cases about the partial fraction expansion. The partial fraction expansion. The case one is all simple pole case. The simple pole means the all is a kind of the real number. So that means fs will be represented in this simple way: s minus p1 r1 plus s minus p2 r2 and s plus pn. I'm sorry, with minus. Then p1 and p2 and pn will be the pole of this system. And here we have some problem. What is Ri? Ri can be written Fs multiply S minus Pi, then S is Pi. Then we get these parameters R1, R2, and Rn. I will give an example. Example 14 and 4-in-1. Let Fs is a S squared plus 7s and 10 and s plus 3. Then we will make this transfer function as the partial the fraction expansions. So we will do is partial fraction expansion. So that will be s plus 3 and s plus 2 and s plus 5. Then we can rewrite here is s plus 2. We have two poles, one poles and two poles. So we write there is a R1 plus s plus 5 and R2. We need to find out. Need to find out. Need to find out these two variables. So that's why we make this equation. This is how to get the Ri in this case. So what is Ri? Ri is S minus P. No. We will do this. First is R1. R1 is S minus P1 Fs and S was P1. So that will be P1 is that is it? S plus 2 and Fs is S squared. Actually this is Fs. This is Fs. S plus 2, S plus 5, S plus 3 at S plus P1. So then there will be limit. So there are variables S plus 5 and S plus 3. Then S of P1 is minus 2. So it will be 1/3. Then why this is R1? Now, I will give you why this is. I mean, for example, what's the meaning of that? That we write here is S minus P1 means S minus P1, S minus P2, and something, right? That will be S minus P1 something, R1 plus S minus P2, R2, S minus P1. So because that we get it, there will be S minus P2 something will be R1 plus S minus P2, R2, S minus P1. And here we apply S is P1, also this is S was P1, then what happened? There will be P1 minus P2 and something will be, because we insert here, will be the 0, the remaining thing is only R1. So we can calculate R1 in this manner. So this is a way to get the R1 The same way we calculate, only we need to know, we got it, R1 is 1 over 3, so we need to R2. R2 will be, because R2 is parameters of s plus 5, so that is fs and s plus 5, then apply s is minus 5. So s plus 5 and fs, this is fs, s plus 2, s plus 5, and s plus 3, and s is minus 5. Your neighborhood, so there will be minus 3 minus a. No. Minus 3 and minus 2. Okay, there will be 2 over 3. So we get it, R2 and R1. So this is the final form here. Therefore, Fs will be 1 over 3 s plus 2 plus 2 over 3 s plus 5. Then what we have to do? We have to know that Ft will be inverse Laplace of Fs. So there will be inverse Laplace 1 over 3 s plus 2 1 plus inverse Laplace 2 over 3 s plus 5 1. So that will be 1 over 3 exponential minus 2t plus 2 over 3 exponential minus 5t. Or t will be, should be larger than 0. So this is the way in when the simple pole case, we get the how to the Laplace inverse Laplace. In second, is case 2. Now this is a simple complex conjugate pole. That means P1 will be minus A plus JB, then P2 will be minus A minus JB. We call this is a simple complex conjugate pole. Let Fs will be S minus P1 R1 and plus S minus P2 and R2, and we have F3S. Then if the P1 and P2 are the complex conjugate, then we can rewrite here is S minus minus A plus JB is something plus S minus minus A minus JB and something plus F3S. And here, because the pole is conjugate complex number, so the R1 and R2 could be the complex number. So we in this time we make R1 is C plus JD and R2 is C minus JD. Then Fs can be rewrite written like that. This is because of that. Can rewrite S plus A minus JB and S plus A plus JB and C plus JD, S plus A plus JB plus C minus JD, S plus A minus JB, and F3S, this. Then we rewrite this formula more simply. That will be S squared 2AS plus A squared plus B squared and 2CS plus 2AC minus BD plus F3S. F3S means that in the other terms, in the arbitrary other terms, so you can rewrite this as S squared plus 2AS plus A squared B squared and K1S plus K2. So let K1 is 2S, K2 is 2AC minus BD plus F3S. Then anyway, can do this. We will discuss on later. Anyway, we can rewrite this. And no, not this. We can rewrite this more simply. So that will be S there will be one terms and other terms. So S plus A squared plus B squared and we this. So to see S plus A minus 2BD plus F3S, then we make it 1 and 2 and 3. So we rewrite this as 2C S plus A squared plus B squared S plus A minus 2BD, no, not 2D, S plus A squared plus B squared and B plus F3S. Okay, this is Fs. This is a Fs. So to make an inverse Laplace of this, then first term of this is Laplace inverse to see S plus A squared plus B squared S plus A. This is very familiar. You can find out that we need to use two property of the Laplace transform. We already mentioned about that. That is Laplace sine omega t was s square omega square omega. Laplace cosine omega t was s square omega square s. And Laplace there will be f. That's it. We will do 3 terms. So you know that this will be 2c, and you know this is very familiar form of these terms. So it will be cosine omega is bt, but there are some variable s plus a, so we're adding exponential minus at. So in the same way, we get that get this to the s plus a squared plus b squared b, and there will be to the exponential minus at sine bt. So therefore, in this case, inverse Laplace fs will be 2c exponential minus at cosine bt minus 2d exponential minus at sine bt, and plus other things. So this is a way to inverse the Laplace in the case of the pole has a complex conjugate pole. So we have example here. Example 14, 4 and 2. The fs is given that s squared now I think we use another page. S squared plus 6s plus 10, and it's plus 2 and 10. We need to inverse Laplace about fs. So to do that, at first, what should we do? At first, we need to do partial expansions. To do that here, because there are second equations, first order equations, so we have 3 terms. That will be, to do that, we rewrite this is, square 6s plus 10 equal to zeros. We need to find the pole. Pole will be minus 3 plus minus, there will be minus 3 plus minus j. So P1 will be minus 3 plus j, it will be minus 3 m minus j. So this can be rewrite here is s plus 3 minus j, s plus 3 plus j, and s plus 2 and 10. So we rewrite this as a 3 terms. S plus 3 minus j r1 plus s plus 3 plus j in r2 and plus s plus 2 and r3. So complete this partial expansion. So we need to find out r1 and r2 and r3. So to do that, what should we do? Next is need to find out r2. Next. R1, R2, R3. The first R1 will be S plus 3 minus J Fs, and S will be minus 3 plus J. So then S plus 3 minus J and Fs is S plus 3 minus J, S plus 3 plus J, and here S plus 2 and this and 10. Then S is minus 3 plus J. Then we'll remove in this manner. Then our result will be two J and minus 1 plus J and 10. So there will be minus 5 over 2 plus J 5 over 2. In the same manner, we can calculate R2. R2 will be S, because R2 is that values, so we multiply the atoms. S plus 3 plus J and Fs, S will be minus 3 minus J. So to do that, S plus 3 plus J and Fs will be S plus 3 minus J, S plus 3 plus J, S plus 2 and 10. At S will be minus 3 minus J. Also it will be removed here. Then the result will be minus 2J and minus 1 minus J and 10. So there will be minus 5 over 2 minus J 5 over 2. The last thing is R3. R3 is this terms, R3. So we multiply that terms. So S plus 2 Fs, S will be minus 2. So S plus 2, S plus 3 minus J, S plus 3 plus J, S plus 2 and 10, S will be minus 2. So eliminate each other. Then the result will be minus 1 minus j and 1 plus j and 10, and that will be 5. Okay, so finally we get, so I think we need more space. So then therefore fs will be s minus 3 plus j, and r1 is, this is r1 minus 5/2 plus j 5/2 and plus s minus 3 minus j minus 5/2 minus j 5/2 plus s plus 2 and 5. So we need to simplify these equations. So to do this, we'll rearrange these as you want. So what we do is, s minus 3 plus j, s minus 3 minus j, then minus 5/2 plus j 5/2 and s minus 3 minus j plus minus 5/2 minus j 5/2 s minus 3 plus j plus s plus 2 5. Then we need to simplify this. It will be s squared plus 6s plus 10, and there will be minus 5s minus 20 plus s plus 2 and 5. Then you need to modify these terms as like that. S squared plus 6s plus 9 plus 1 and minus 5s minus 20 plus s plus 2 5. So it will be s plus 3 squared plus 1 squared and minus 5 s plus 3, then plus s plus 3. Okay. We need to move a little bit. We need to move a little bit. We need more space. Okay. Square plus 1 square, and because this is minus 15, so limit is minus 5 plus s plus 2 5. Then it's very simple. We have 1 terms. Therefore inverse fs will be inverse of that. What is that? Minus 5, this is a cosine, but exponential minus 3t cosine omega is 1t. This second term is minus 5. This is a kind of this is 1, right? Exponential minus 3t, and this is sine. sine 1t. And last thing is plus 5 exponential minus 2t. And t is over 0 second. So this is the way to inverse Laplace when the Laplace transfer function has the complex pole. The third case is case 3 is repeated pole. For example, Fs as a S minus P1 R1 plus S minus P1 square R2. In this manner, there were S minus P1 Q and RQ plus S minus P plus 1 and R Q plus 1 blah blah S minus P and Rn. I mean, there are some poles, but pole has in this manner, the pole is complicated. I mean, pole is repeated. Then how to get these R? That's the question. So to get that, the formula is RQ minus K is 1 over K factorial and ds K dk S minus P1 Q and Fs, and S will be P1. This is a way to calculate the parameters in R. So as example, I will show you how to solve the problems. So example 14 and 4 and 3. Fs is a S plus 1 square, S plus 2, and 4. As you see, this is a repeated poles. And pole is, the pole is places is minus 1 and minus 2. But minus 1 is the square. So that means the repeated pole, the second of the pole. We call this is a second other pole. Anyway, so we partial fractions, there will be S plus 1 R1 plus S plus 2 R2. That's it. This is not enough. Why? Pole minus 1 is the second order. So we need one more parameters. So this is not good. This is not good. What should we do? We should do this is S plus 1 R1 plus S plus 1 square R2 and S plus 2 R3. Because we need two parameters R1 and R2. Why? Minus 1 pole is the second of the pole. So we need two parameters. So to get that, we need to find out R1, R2, R3 respectively. The simple problem is R3. So R3 is S plus 2 Fs, and S will be minus 2. So it will be S plus 2, S plus 1 square, S plus 2, and 4. S will be minus 2. So it will be minus 1 square 4, it will be 4. Next is R1. Next is R1. So in the case of R1, because based on this general form of that, we can use it. Because in the case K is 1, so 1 factorial 1, and first dsd s, because it is s plus 1 1 square and s plus 1 square, s plus 2 4, and s will be minus 1. So there will be like that. Then it will be minus s plus 2 square 4, and s will be minus 1, so there will be minus 4. And next is R2. Next is R2, and R2 is, we need to use the same formula. So in this case, you can use it. Okay. In this case, I mean, you need to know that you need to compare this form and this situation. In this case, Q is 2. In here, Q is 2. And K, K is 1. In this case, Q is 2, but K is 0. So therefore, because K is 0, so means 1, and because K is 0, is no derivative, so it will be S minus a plus 1 square, and S plus 1 square, S plus 2, and 4, and S will be minus 1. So it will be eliminate each other, and the result will be uh, 4. So R1 is minus 4, R2 is 4, R3 is 4. So we apply that here. Then Fs rewrite is S plus 1 minus 4 plus S plus 1 square 4, and plus S plus 2 4. This is complete of the partial expansion. Then what should we do? We have to do inverse Laplace. Will be inverse Laplace of s plus 1 minus 4 plus inverse Laplace s plus 1 square 4 and plus inverse Laplace s plus 2 and 4. Actually, I don't think it's very simple, but you need to know about these things. This is very simple and this is simple, but it'll be a little bit complicated, but then you can use these terms. But that is we'll use blue ones. Laplace t will be 1 over s squared, right? And Laplace exponential minus at ft will be f s plus a. We will use two things. Okay, that means the first thing is, this is very simple, minus 4 and exponential minus t. And second thing is, we will use that. This is square, so we will use these ones, because this we will use square. S square 1 over s square. So that will be kind of a 4. But we'll use that. Exponential minus t, but t. And last thing is 4 exponential minus 2t. So this is the result of the inverse Laplace in the repeated pole. We will have another example. Example 4 and 4. So especially this improper rational function. The rational function is all parameters is a rational number. Then we call the rational function. What is improper and proper? The proper means is an order of d is higher than order of n, and improper is the reverse. Order of n is higher than order of d. So that is improper. So this is quite interesting. So this example, fs was s squared plus 5s plus 6 and 4s3 plus 15s 2 plus s plus 3. In the order of the denominator is smaller than the other of numerator, so we call this as an improper function. So we can rewrite here then what should we do? The first step is we need to change this rational function, improper function to proper function. How can you do that? We should do this is we need a longer space. S squared plus 5s plus 6 and 4s and s squared plus 5s plus 6 and minus 20s minus 20s and minus 24s and plus 15s squared plus s plus 3. Then there will be s squared plus 5s plus 6 and 4s, s squared plus 5s plus 6. This is for about this, right? That's it. And we calculate the main thing is minus 5s squared minus 23s plus 3. The only main thing is improper. Because of that, you can rewrite this is 4s, right? This will be the same things like that. And plus s squared plus 5s plus 6 minus 5s squared plus minus 23s plus 3. And can rewrite this 4s plus s squared plus 5s plus 6 minus 5 s squared plus 5s plus 6 and plus 25s minus 3 and minus 23s plus 3. This is this, and the remaining thing is here. So we can remove this, so there will be 4s minus 5 and s squared plus 5s plus 6 and 2s. That's it. So we have this term and other proper rational function. So we rewrite here 4s minus 5 and plus s plus 2, s plus 3 and 2s. Then there will be, that could be the partial expansions. 4s minus 5 plus s plus 3 6 minus s plus 2 4. You can do that by yourself. So fs, we press the here, rewrite right here, and here we can use some good property. Where's that? The inverse Laplace of s will be dt d delta functions. So then fs will be inverse Laplace 4s minus inverse Laplace 5 and plus inverse Laplace s plus 3 6 minus s plus 2 4. Then because of that, so there will be 4 dtd delta functions and minus 5 y the Laplace of 1, delta t will be 1. So 5 delta t and plus 6 in the case is exponential minus 3t and minus 4 exponential minus 2t when t is positive. So this is the way when the transfer function is improper, then you divide the term is the proper functions and other things. Then you can transfer the Laplace transfer function to the time domain the functions. Initial and final value theorem. The initial value theorem in Korean is 초기급 정리. That means that we can gather f0 will be actually 0 plus is limit t go to 0 plus and ft. That value will be same with limit s go to infinity and sf. And the final value theorem in Korean is 최종급 정리. Then that is f infinity will be limit t go to infinity ft. It will be same with s go to 0 s fs. So I will give a proof of this. First, we will start proof of initial value theorem. The last step is SFS. Now, this is S integral to 0 to infinity and ft exponential minus st dt. So this is the same with minus integral 0 to infinity ft and dtd e minus st dt. So that can be represented in the ft minus st from Notice that here, ft exponential minus st, and the derivative of that is dtd ft and minus ft is s exponential minus st. So I can do that. So if we integral of the here, then ft exponential minus st will be integral dtd ft. Oh, I am losing something. Exponential minus st dt minus integral ft se minus st dt. So that will be this. So from here, okay, we write this here. So from here, integral ft s exponential minus st dt will be integral dtd ft exponential minus st dt minus ft exponential minus st. So that will be this. So that will be right in there. So because of minus, we can define it here, arrange as 0 to infinity to 0 to infinity to 0 to infinity. But because of minus, we change this as infinity to 0 and plus integral 0 to infinity dtd ft and exponential minus st dt. So when the t is infinite, it will be the 0. So the remaining thing is f0 and plus integral 0 to infinity dtd ft exponential minus st dt. After that, if we go to the s to the infinity, s fs is limit s go infinity f0 plus integral 0 to infinity dtd ft exponential minus st dt. So because s is infinity, there is infinity, so it'll go to 0. So remaining thing is f0. Therefore, if we go to s, go to infinity, then sfs is f0. This is the initial value theorem. Next, we'll do the final value theorem. We can use very similar things. Final value theorem. We did it here. As from the previous proof, SFS was f0 plus integral 0 to infinity dt the ft and exponential minus st dt. Now let go to the s go to 0. SFS is s equal to 0, f0 plus integral go to infinity dt d ft, and s equal to 0, that means 1, so dt. Then what's the value of that? That is f0 plus integral 0 to infinity dt d ft dt. So it will be f0 plus ft from 0 to infinity. That value is f0 plus f infinity minus f0. So there will be f infinity. Therefore, limit s equal to 0 as f as the same value of f infinity. That is the final value theorem. So that because of these theorems, we can solve very simple calculations. Without these theorems, it will be very complicated problems, but using that, we can get the solution very easily. Let's give some example. 14-5 and 1. Let Vs is a Laplace of Vt, and that was s squared plus 9s plus 34 2s squared plus 33 30s plus 136. So we want to get the Vt. What is a Vt? So to get here, we need to get some variables of initial values. Then we can calculate V0 very simply. How can do that? The limit s go to infinity and s vs. So limit s go to infinite and s squared 9s 34 2s squared plus 30s plus 136. So it will be s go to infinity 2 plus 30 over s plus 136 s squared and 1 plus 9 over s plus 34 over s squared. So it will be 2. So this is initial value of v. And we get the final values. V infinity is s go to 0 and s vs. So limit s go to 0, s squared plus 9s plus 34 2s squared plus 30s plus 136. There will be 136 over 34. That will be 4. Then next we get the Vt. Then Vt is inverse Laplace of Vs. Then Vs will be we have similar things. There will be, 1 and 2. So we have as R1 and plus s squared plus 9s plus 34. But in this case, we can gather R2s plus R3. So anyway, using the simple calculation, we got that their value is S4 minus s squared plus 9s plus 34 and 2s plus 3. Therefore, it can be rewrite 4 over s minus s plus 3 squared plus 25 and 2s plus 3. Therefore, Vt is inverse Laplace 4 over s minus 2 s plus 3 squared plus 5 squared and s plus 3. So it'll be 4 minus 2 exponential minus 3t, and do be cosine 5t. So you need to check the initial theorem and final theorem. The initial value theorem and final value theorem. Initial value was 2 and the final value was 4. And because we get these voltage equations, so Vt at t equal to 0, then 4 minus 2 exponential minus 3t cosine 5t in t equal to 0 will be 4 minus 2 equal to 2. The same result. And we get the final value t to infinity. It will be 4 minus 2 exponential minus 3t cosine 5t in t is infinity. Because of infinity, it will go to the 0. So there will be 4. Then it will take the same with their values. So the final value theorem is initial value theorem is very exact in the real system. So if they want to know the initial value or the final value, then we don't need to do the inverse Laplace to get the function of the time domain function. Just calculate this simple equation, you can get the final values and initial value. Very simple.